So, Shabab, let's go and continue the solution for our problem that we started. So if you recall this problem, just to remind you, we have this link, okay, which is subjected to a 4 kilopound and minus 16 kilopound of force as a fluctuating load. We have fillet over here, that's a fillet, and we have a hole. Okay, very common in the industry, and we know that these guys are going to cause stress concentration. So what did we do? We went ahead and, just to review with you, we found the ultimate strength, the yield stress, and then we found the SE prime, which is the uncorrected endurance limit. Then we got the KA. KB was 1 because this was an axial loading, and then KC is 0.85 again because it's axial loading. Then we found SE. After that, Shabab, we used the geometry, the W1, W2, the radius, and so on to find KT. I think يعني it's مو معقول إن أنا أعلمكم كيف تطلعوا KT. It's very simple. When you find KT, you go to the figure 620, and you can find Q, and from the Q you can calculate KF. Then we calculated the maximum stress, the minimum stress, and the amplitude. And when we calculate the amplitude, we multiplied it by the stress concentration factor, because this is what the fatigue stress concentration factor is going to do. It will amplify the amplitude as well as the mean. Now, when we found the amplitude and the mean, what we can do, we see that the mean is negative. If the mean is negative, ya shabab, I have a mean stress. So if I have a mean stress, it means I am now thinking Gerber, Goodman, but because it is negative, we told you that those mean stress, you remember the curve which was like this, and the data was scattered over here and right there. This was the defining line for sigma mean equals to 0. If you are here, you use Gerber, Goodman, and others. If you are here, the judging factor is 1, which is how much is the amplitude you are applying and how much is it comparable to the endurance limit. But in fatigue, and this is very important to practice, you must do it even in the project, ya akhwan, in the exam, is before you think about fatigue. Now, by knowing the maximum stress, you need to check is it going to yield? Now, be careful. When you have sigma, I mean, I'm not going to go back to the slide. I'm going to write it down here. Sigma maximum was 3.2 kilopound. Sigma minimum was minus 12.8 kilopound. Do you understand? Now, in order to check yielding, in this one, the material AI, SI, we can easily assume that these materials has a symmetric tension compression behavior. يعني معناها أنت if you reach the yield stress and tension, or you reach the yield stress and compression, you will have yielding. So in order to check the yielding from the first cycle, okay, what are we going to do? We are going to, I mean, this is NY. N means factor, safety factor, and Y stand for the yielding. And then what I'm going to do, I will divide the yield stress by sigma minimum. Now remember, if the maximum is more as a magnitude, I will divide by sigma maximum. But here I need to divide by sigma minimum, and I put the absolute value, because there is no meaning of a negative factor of safety. Actually, there is nothing negative here. It's a stress, but it is compression. That's it. That's the meaning of negative. So I will put the yield. The yield was 54 kbsi, and then the absolute value of a 12.8. Remember, I put the minimum, not the mean. And then what I get 4.22. This is safe. It will not yield. This means it is safe.
Doctor.
Okay. Yes.
Did you put 12.8 because it's higher in magnitude than 3.2?
Of course, yes. With respect to the material يا شباب شو اللي صاير؟ اللي صاير كذا إنه during the tension reversal the maximum stress goes to how much? 3.2. And in the compression it goes to minus 12.8. Now احنا ايش نعتقد؟ نعتقد انه ال stress strain curve is like this. Do you see? Now the distance from here to there, okay, is the difference between the yield, which is 54, and the 3.2 is just little right there, okay? But Anna, I did not draw it in a nice way. So this is a 12. This is 3.2. This difference is a lot between the 3.2 and 54. Here, this is a 12, and تخيل, minus 54, which is the yield in compression. So you are far away from it. That's what are we trying to say. Do you understand that?
Yes.
Okay, good. Now, what are we going to do? I need more extra slide, ya shabab. Now, what are we going to do? We are going to find SA, which is, we found SA. Let's just admit your brother here. So then what are we going to do? We are going to use the relation. Do you remember from our discussion last time, we said that SA over SE equals to 1 is kind of the criteria to if there is a negative mean. So what are we going to do? This means that SA is equals to SE. صح ولا لا? What is SE? We calculated it was 24.4 kbsi, right? So I shouldn't write I over here. kbsi. Okay. Now, if this is the stress strength now, the amplitude strength, then in order to find the factor of safety for fatigue, all what I need to do is to divide the amplitude strength by the amplitude I am applying. Now, the amplitude we are applying is 15.2. We calculated it from here. Look at it, 15.2. Now, and this one is the same as the endurance limit, which is 24.4. So what I'm going to get, I will get 1.61, which is way less than the yield factor of safety, but it's still safe. Good, ya shabab? Are you good?
Yes,
so,
yes.
باختصار يا أخوان, if you have a negative mean stress, the factor of safety NF is equal to SA divided by sigma A. What is SA? SA is مفروض إنه يكون the same as the endurance limit. خلصنا. That's it. Now, what I am going to do, I will skip يا أخوان the next part because it is a repetition of the first one. اللي هو dealing with the whole. شي راح نسوي؟ راح نجي ونطلع ال KT and then we need to find the Q and then from Q we can find and KT we can find KF. By finding KF يا شباب, which is going to be different, sigma A will be equals to the new KF for the whole multiplied by what? By sigma max minus sigma minimum divided by 2 and sigma mean, which is equals to KF sigma max minus sigma minimum over 2. That's what you should do. And when you do so, طبعا انتبهوا يا شباب, الملاحظة هنا إنه الهول when you look at the plate هو طبعا في فلت هنا صح ولا لا؟ So but يا شباب اللي جاكم في السؤال إنه you are applying a load, a force. الفورس يا شباب is applied everywhere. The stress which is generated because of the force is different depending on the area. So when you focus only on this, look what happens. Now we need to analyze this part. Now this part is rectangular like this, but what are we going to do? We are going to consider this part اللي عند الهول. Now if we consider this part يا أخوان إيش اللي راح يصير؟ اللي راح يصير إنه الاريا بتكون كذا. There is a hole here. So the area is this that we will use. And now, just to show you, sigma maximum is going to be, what was the maximum force? It was 4. So this is 4 kilopound divided by the thickness. صح؟
Doctor, isn't the maximum 16? It's fluctuating between 4 and 16.
No. It was 4 and minus 16. You understand?
Yes, but still a force. The minus is indicating compression only.
إيه صحيح بس يا فارس لازم أنت عشان المعادلة تفهم هل أنت عندك positive mean ولا negative mean. You need to make this one minus 16.
Yes,
you divide by the area and this one you divide by the area. لازم.
Okay.
الآن السؤال الآن what is the area? Now let me go back to the figure. The area, what does it say here? It says that W1 is equals to how much يا شباب? Is 3.75. Do you understand? So, and look, what is small d? It is 0.75. What is h? اللي هو thickness? It is 0.5. So, the area which I am going to use to calculate the stress is this. It's going to be 0.5, which is the thickness, multiplied by 3.75 minus how much? Minus 0.75. عشان أطلع اللي لونها أخضر فقط. فأنا أقول 0.5 مضروبة في 3.75 minus 0.75. That's the area. In here the area is exactly the same. 0.5 multiplied by 3.75 minus 0.75. Do you understand that? خلاص أنت لما تطلع شوف لما تطلع الماكسيمم stress and you calculate the minimum stress, it's over. You need to find now the amplitude and you need to find the mean. Once you find the mean, you will know, do I have a positive mean or a negative mean? You will end up having a negative mean here, the same way. The values are different because the areas are different, but it will end up being the same thing. Actually, interestingly, ya shabab, just to let you know, if you go and find the solution in the slide, you will find that NF is equals to 1.61, which is the same. So from fatigue perspective, you don't know which one of the two is more dangerous. And if, for example, after some many years, okay, which one of them is going to develop a crack before the other? You don't know. This is what the factor of safety is telling us. They are both having the same factor of safety. معناها انهم from a risk point of view they are equal, the same. Okay? But مثلا على سبيل المثال لو كان مثلا الهول if the hole has a factor of safety of, for example, 1.2 and the fillet has a factor of safety of 1.61. اوكي. هنا انت تجي حق الكلاينت وتقول له في اذنه اوكي يا شباب خل عينك على الهول ها. Be careful. You may not tell him watch out the fillet. تقول له أول شيء طالع الهول. And this is the reason. It's not a joke. It's what the calculations are telling us. Do you understand? Okay. Now, what is important يا شباب? Now, the next part is what happens if we have a cyclic shear loading. Cyclic shear is a little يعني يا شباب rotating bending will produce normal stresses, partly tension, partly compression. And if we apply cyclic axial loading, we are also applying normal stresses. الفرق فقط إنه in tension loading, you have always tension and or always compression. In bending, you have tension and compression at the same time. Now, and we indicated through the figures, if you remember this figure is very important, that positive mean is dangerous. And when we talked about positive mean, we talked about sigma. It's a positive normal mean. Normal, يعني normal stress. And here it is negative. We did not talk about tau. Okay? And the reason is this. أول حاجة في التورجن يا شباب there is no meaning like the compression إنه when you twist a material clockwise or you twist it counterclockwise you will have a different يعني مثلا في الشير torsion ما في شيء اسمه one curve like this another curve like this and they both have different yield وتقول هذا counterclockwise وهذا clockwise. No. That doesn't happen. It's the same. You understand? It's the same. And and not only this, I'm gonna read with you the first paragraph. It has been found, it had been found experimentally that the existence, the presence of a torsional steady stress component not more than the torsional yield strength has no effect on the torsional endurance limit. What does this mean? It means if I go and make a machine which can apply cyclic torsion, and then I applied tau mean and tau A, good? Such that tau mean is less than tau yielding, less than the shear in yielding. It turns out that the mean here does not change a lot. It's not like the positive mean. يا شباب الpositive mean add 10 megapascal, 20 megapascal, and then it will change the endurance limit automatically. But with torsion, it's a little bit different, actually a lot. So what is now the idea is this: how do we deal with torsional fatigue? Now, what we are talking about is torsion only, no other loading. We're not talking about tension and torsion, only torsion. يعني تخيل ان واحد جاء وقال لك والله انا عندي part of the machine which is only subjected to torsional cyclic loading. Now, does it have a mean torque? Does it have only an amplitude torque? Both. Now, how do we deal with it? Number one, what do? We multiply, okay, the ultimate strength for torque, okay, by 0.67 of that for tension. يعني in order any equation in the fatigue, okay, يا شباب, that has an ultimate strength in tension, we replace it with ultimate in torque, in torsion, by multiplying it by 0.67. 0.67. So if I want, for example, to use Goodman says we have to divide sigma A divided by SE plus sigma mean divided by SUT, which is equal to 1 over N. So what are we doing here? We're saying go and multiply this one by 0.67. When you multiply SUT by 0.67, you are like converting it into a shear ultimate strength. And replace this now with tau. خلاص صار tau. Now, this one is tau A. What is this, ya shabab? This is the endurance limit. So, for the endurance limit, how do we find the endurance limit in torsion, ya shabab? You remember? We said, ya akhwan, that we have 0.59 factor, which is Kc. If we apply that 0.59 on the SE prime, it will become SE corrected for torsion. So we can convert this one for SE torsion by applying Kc equals to 0.59. And with that, we just converted the endurance limit for torque, and we converted the SUT for torque, and this is how we can use the equation for torsion only. Now, what about if any equation like the ASME elliptic, for example, or Söderberg, they do not use SUT, they use SY, then if you remember from chapter 5, we told you that the von Mises or the distortion energy equivalence of the yield is 0.577. So what do? We take the yield in tension, we multiply it by 0.577, okay? And then it becomes a yield in shear. And that's how we convert it. Do you understand? Now, what I am going to do next class, I promise you to get back on a few issues on fatigue. One of them was how to use the KD, okay? Like I told you that there are two methods for using KD, and I promise you to bring you an example. So I will bring you example about that. I will also bring you example about this. So when I mean by example, it's just an example. I'm gonna explain it. I'm not gonna solve it, okay? Because next class, we need to start chapter 7, which is, by the way, going to be very important for your project. It will help you, okay? And also, we'll talk about the master diagram, maybe today if we have time. But this is in general how to convert the strength for torsion loading, okay? Now, what do we want to do is this. We want to talk about combined loading. Now, in real life, you hardly find something which is subjected to uniaxial. Uniaxial يعني either tension or torsion. In reality, life is more complex, and there are always the two loadings together. Okay? So, احنا تعلمنا من chapter 5 بأنه whenever you have multi-axial loading, you need an equation, a factor, a criterion, anything that combines all the effects and make them in one number. Now, if you realize with fatigue, we always care about two things. Two things, يا أخوان. Two things. Amplitude and mean. Now, In chapter 5, we told you we have the maximum shear stress theory, we have the von Mises theory. Most common is the von Mises. And that's what we are going to do. Now remember, von Mises, ya akhwan, what does it do? It takes the multi-axial loading state and it converts it, ya shabab, into a uniaxial normal state. Why? منين؟ كيف تعرف الحقيقة هذه؟ لأنه von Mises sigma prime is compared with what? With SY. معناها انه يقول لك تعال give me sigma x, give me sigma y, give me sigma z, give me tau xy, give me tau zy or tau xz, all of them, put them in here, and then I am going to judge based on one single value which is obtained from tension specimen. Now, the beauty is this. If we use von Mises to take sigma prime A, we put an amplitude, and then inside it, we put FA, the stress coming from axial cyclic loading. And we put inside it MA, the stress coming from bending loading. And we put inside it TA, which is the torque amplitude, all together. What is it going to give me? It's going to give me an equivalent amplitude. And then I go and I use the same von Mises equation to put FM, which is not the radio station, the mean force, and then moment, the mean moment, and the mean torque. شو بيطلع لنا؟ حط كل هذا inside here, I will get sigma prime M. Now, look how interesting this is. When you put sigma M and sigma A, now, if you have a positive mean stress, you can just put sigma prime A divided by SE plus sigma mean prime divided by SUT, which is equals to 1 over N. And this is what? This is Goodman. I don't need to change this. I don't need to change this. Why? These guys were produced for cyclic normal, not torsion. I don't need to do torsion here. Do you understand? So I can use the tensile properties in order to judge. So the same, I can use Söderberg, sigma prime A over SE plus sigma mean prime over SY, which is 1 over N. Beautiful, right? So the question is, how do we do that? Now, look, we will answer multiple questions here at the same time. Sigma A prime, this is the equation for it. Very beautiful, everything you need. Look, it is KF. Now, what if you don't have a notch? KF will be 1. خلاص, هذا KF for bending. Do you understand? Now, and then sigma A, the amplitude coming from bending. صح ولا لا? Whatever the amplitude is, coming from bending. And then, طبعا يا شباب تعرفون كيف تحسبون الامبليتيود سيجما صح؟ خلاص سيجما for bending is equals to M, فتحول الام إلى MA. طلع المومنت amplitude multiplied by C over I. خلصنا. Now, do you remember يا شباب, back like a week ago, we told you when you have multi-axial loading, KC should be equals to 1. And we told you that the reason for this is because we are going to adjust for it by another way. Now, this is the other way. Look carefully. The amplitude of the axial loading, which is, by the way, axial loading is F A over A. The force amplitude divided by area. Now look, we are dividing it by 0.85. That 0.85 is the factor we use to adjust for axial loading. And it is embedded here. That's why we are fixing it right here. Understand? Square, that's a square. And then 3. That 3 account, ya shabab, for the adjustment, okay, of the torsional loading inside the state. And here, طبعا يا شباب, this is KF for axial. And then we have KF for torsion multiplied by tau A. Tau A is just like TA, the amplitude torque, multiplied by R divided by J. Good? خلاص. Down, the same equation. You just change A with M. So this is the mean. This is KF for bending. Bending الKF يا شباب ما لها شغل بamplitude ولا mean. It has nothing to do with them. So you will have only sigma mean, which is M mean C divided by I, and then KF axial multiplied by F mean divided by area. And then for torque, we will have T mean divided by R over J. Good. Now, let's look how are we going to deal with this. طبعا هذا شرح يا شباب للي أنا قلته إنه once you find sigma A prime and you find sigma M prime, you're done. All what you need to do now is to put them into Gerber if it is a positive mean. So let's look at this very interesting example. A bar of steel has a minimum properties. Now look, in this kind of problems, خلاص, I think you are, you know how to find the endurance limit. So what did I do? I gave you the endurance limit, the corrected one. هذه أفضل gift, the best gift you can get in a quiz or exam. I don't need to bother you. I don't want you to calculate it. So, but I want to remind you about one thing. One thing. This SE this SE was found by saying KA, KB, KC, KD, KE, KF multiplied by S prime. S prime is found by, let's assume, 0.5 SUT. KA is the factor for the surface. It has nothing to do with the loading. Is it cold drawn, hot rolled, whatever? KB now is what? We will use KB, okay, for multi-axial loading. And I'm going to talk about it later. KC is equal to 1. You must put it equals to 1 if you have a multi-axial loading. And you will see that this is going to be adjusted later. So I am going to come to calculating SE prime, inshallah, in the next class. As I promised you, I have a few points. I will explain them to you. But for this time, this is SE, this is SY, and this is the ultimate strength. Look what it says. It says the bar is subjected to a steady torsional stress. Oh, this problem is so easy because he gave you tau M, which is equal to 13 megapascal. What is a steady? يعني steady, fixed. And that's the mean stress. It is fixed. It is not an amplitude. Look, an alternating torque, which is equal to 69 megapascal, and an alternating bending stress, which is sigma for bending, A, let's say bending, which is equal to 83 megapascal. We want to find the factor of safety guarding against static failure and against fatigue using Goodman, Gerber, and the Azmi-Leipzig. That's the problem. Okay. Now this is the first time we use those criteria. we didn't use them before in example. So let's see how we are going to do them. Okay. Now, first of all, we are going to go to the equation sigma A prime, which is equal to. Now, I don't have axial loading. I have sigma from bending. And there was nothing about Kf, no stress concentration factor, so it is 1. So if I go back to this equation, what will happen? Look what will happen. I'm just going to show you what will happen. Now, this one is 1. This one doesn't exist because there is no sigma because of axial loading. And look, I actually need to do it for both. Okay. And this one is equals to 1. That's for the amplitude. For the mean, sigma mean was not given. There is no sigma bending mean. So it is 0. And there is no axial. It is 0. And this one is equals to 1. And we have a mean torque only. That's possible. Why not? That's possible. So what will happen is this. Now, when I solve this, look what will happen. Sigma A prime will be equals to sigma A square plus 3 tau A square under the square root. So how much is this one? This is going to be 83 square plus 3 multiplied by 69 square under the square root. And this is going to be 145.5 megapascal. Sigma mean prime is equal to what? Sigma mean square plus 3 tau mean square under the square root. And this is going to be 0 because we don't have any mean moment. And then 3 multiplied by 103 square under the square root. So what would I get? 178.4 megapascal. Yes, Ali, do you need anything?
No.
Okay. Now, when I found sigma A and sigma M, I can add them together and find the maximum. صح? But I'm going to show you that I can find sigma maximum prime using von Mises by saying that sigma maximum square plus 3 tau maximum square under the square root. So what should I do? I should take this plus the, what is it? I should take, sorry, ya shabab, not this. Sigma maximum is coming from the bending. So the bending, we have an amplitude of 83, but 0 mean. لأنه دائما يا شباب, sigma max is equal to sigma A plus sigma M. Now, what about this? This one, I have tau amplitude of 69 and tau mean of 103. So if I plug them in and I square them, I will get a maximum stress of 309.2 megapascal. صح? Now, what should I do? I do the following. I go Ny is equal to what? The yield stress divided by sigma maximum prime. We just calculated sigma maximum prime. And sigma maximum prime was 309.2. What was the yield stress given in the problem? It was 413. So how much I get? I get 1.34. This is the factor of safety against yielding. Now, if I want to use Goodman, okay, the factor of safety NF is equal to 1 over sigma amplitude, which was 145.6 divided by the endurance limit was 276, plus the mean stress, which is 178.4 divided by the ultimate strength, which is 551. And when I do this, I will get a factor of safety of 1.18. very little, but it's still safe. Then what should I do? I use Gerber. Gerber will give me one factor of safety of 1.47, and then ASME will give me a factor of safety of 1.47. Both of them, ASME and Gerber, gave me the same value. And I would like to tell you that if you go to the slide, you will see me drawing the criteria. And you will see that based on this problem, this is what will happen. You will have the load line coming like this. And here, both Gerber and ASME will give you the same value because they are on top of each other. If the line is here, then each criteria will give you different value. But here, Goodman gave you different one, but these two gave you exactly the same value. Do you understand, ya shabab? This is the end of the, not the end, there is a little bit more. I will explain it inshallah next class before we start chapter 7. I want to now quickly, ya shabab, ask you to turn on your webcam quickly within 1 minute. I'm sorry for being late. I need to take your attendance, ya shabab. Okay, Faisal?
Yes, present.
When I call your name, you can leave. Yusuf?
Present.
Yusuf?
Here.
Okay. Hamad?
Yes.
Ali?
Yes.
Tani? Yusuf?
Yes.
Majid? I
Yes.
can see you. Hussein? Ali?
Yes.
Hussein? Muhammad?
Yes.
Where are you, Muhammad?
Yes.
Okay. Hassan? Ayash?
Yes.
Can see you. Mubarak?
Yes.
Ahmed Ghazali? Where are you, Ahmed? Ali is here. Mu'jib? Where are you, Mu'jib? No. سلطان الحربي؟
موجود يا دكتور.
اوكي. عبد الله؟
يس موجود.
سلطان؟
موجود.
وشان؟ عبد الرحمن؟
موجود دكتور.
خالد العتيبي؟
موجود دكتور.
عبد الله العوفي؟
Yes.
فارس؟
موجود يا دكتور.
ثابت؟
حاضر.
علي رمضان؟
موجود دكتور.
هاشم؟
موجود.
ماجد؟
موجود.
محمد؟
موجود يا دكتور.
أحمد سلطان؟
موجود دكتور.
مشعل؟
موجود دكتور.
مشعل يا وليد؟
موجود دكتور.
وليد اوكي. محمد باراشيد؟
موجود دكتور. موجود.
اوكي. عبد الله؟
موجود دكتور.
and أحمد.
موجود.
Okay, thank you so much يا شباب. Have a nice weekend.
دكتور
Yes?
عندك office hour today؟
Yeah, of course.
نفس الوقت من 1 تنتهي.
Yes.
تمام يعطيك العافية.